All right. So after doing a crash course in R and a crash course in statistics, we are finally ready to begin our journey in econometrics. And we're going to start this journey by going over the simplest version of the regression model, which is Simple Regression Model, or for short, we call it SRM. Okay. And so the plan is we're going to start with simple regression model, and then down the road, we're going to extend it using multiple explanatory variables, and we call it multiple regression model. But as starters, let's go to the whiteboard and talk about the intuition of what is simple regression model. Remember, we had, I think in the first couple of sessions, we talked about different econometrics models, and one of them that we explored was basically we said, okay, let's try to predict what is wage. And we said, okay, it has something to do, it must depend on maybe education, maybe age, maybe it depends on gender, maybe it depends on the experience. It may also depend on talent and etc. Right? So some of these variables, we cannot collect information on them. So for instance, how can we quantify talent? So this is a challenging one. So we either need to come up with a proxy variable, or we should give up on the idea of coming up with the relationship between talent and wage, right? So some of them, there is no data. And for some of them, again, for some of them, it's really hard to quantify it, like talent. And for some other one, again, just for example, imagine we don't have information on experience, okay? But we do have information on education, age, and gender, okay? Let's say for any, and of course, guys, remember, there are lots of other things that we call them unknown. We don't know. There are lots of, maybe there are lots of other variables that has something to do with the wage, but we're going to ignore them. So we call them unknowns. Right? So in simple regression analysis, so in simple regression model, is a model that we have one target variable, which is, or one independent variable, which is here, we usually show it with wage, and we have only one explanatory variable. So this y is going to be always one variable, right? So you always have one target, and you're trying to predict that target variable using multiple explanatory variable. In simple regression model, you only have one explanatory variable. So let's say in this example, I'm going to only stick to education. So I'm going to keep the education. So I'm going to rewrite the model like this. Wage has something to do with education, and everything else, I'm going to squeeze them and call it U, which stands for unobservable. Okay, again, I call them unobservables. Right? So this is the simplest version of regression model that we can imagine. Okay, now let's see how can we write the econometric model. Remember, what were the steps? Come up with the econometric model, then specify the model, collect data, and quantify the model, right? So if I want to write an econometric model, we say, okay, wage is equal to some constant beta 0 plus and another constant, we call it slope parameter, multiply education, and everything else that we just call it unobservables, right? And remember, these unobservables can be a combination of many things. Something truly unknown, or some variables that it's hard for us to collect data on, like talent, and some other variables that for some reason, we're going to skip them, we're going to ignore them, okay? So in simple regression analysis, you're going to only stick to one of those variables. So I can write education here, I can write age, I can write either gender, experience, but in this model, whatever it is, we're going to deal with only one variable. one exponential variable, right? So with this information, let's go over the slides and see officially what do we call these things. So there are multiple names for this y, there are multiple names for this x, and so here's our constant, here's our slope parameter, and these are also called our unobserved factors, unobserved factors. All right. So at the end of this chapter, this is chapter 2 from the textbook, we will be able to finally quantify our econometric model. So this is something that we talked about it in previous classes, and now we're able to put some numbers instead of beta 0 and beta 1. So let's figure that out. All right. So the simple regression model, definition of simple regression model is like this. We are interested in explaining, at the end of the day, you want to explain something using econometric model. Explaining y in terms of x. So explaining wage in terms of education, explaining wage in terms of gender, explaining wage in terms of experience, and you name it. Or alternatively, we are going to say that simple regression model studies how y varies with changes in x. So the direction of the causality is important. At the end of the day, we want to see how wages change if we change the education, not the other way around, not how education change if we change the wage, or income versus consumption. How does income change? How does consumption change if we change the level of income, right? Not the other way around. So this is the direction. The direction of the causality is also important. So what are the names, different names that we have for y and x? So our y variable, usually in a standard econometric language, we call it dependent variable because it depends on something else. It depends on one or many other exponential variables or many other independent variables. In simple regression model, we say it depends on one other variable, that's x. So dependent variable y versus independent variable x. If I have multiple x, it's independent variables. So here in simple model, we have only one. Okay, so dependent versus independent. Sometimes we call it explained versus explanatory variable. So we're trying to explain y, and x's are explanatory variables. Sometimes we call it response variable versus control variable. In econometric, this is also very common. People tend to call these x variables control variable. These are different names. It really doesn't matter, how we call them, but just remember, this is the way that we distinguish them. These are just simple names. And sometimes we call it predicted variables versus predictor variables. So these are the ones that we're trying to predict. Y's are the one that we're trying to predict at the end of the day. So we call it predicted variable, and x's are predictor variable. Or finally, again, this is very few people use this one, specifically the regressant. Maybe regressor, yes, but regressant, no, there's not many. Well, at least as far as I know, very few people use regressant. But just I'll put it there for your information. We can also call y as regressant versus x, which is regressor. So whenever I talk about, so I personally use control variables, explanatory variable, independent variables, and regressors sometimes interchangeably during the semester. So don't get confused. Sometimes I call them control variables, and maybe unconsciously I call them independent variable, explanatory variables. We're all talking about these x's, the variables that are explaining something, right? And then we have multiple names for u as well. So we call it error term, disturbance, unobservables, and etc. Okay, but I think the most common ones are the unobservable, so that this u stands for unobservable. All right, so this is the basic terminology in econometrics, in an econometric model, and then let's move on. Let's see how we can interpret those models. So let's stick to our simple example of wage. What happened? Sorry, why it keeps, yeah, wage is equal to, let's say, beta 0 plus beta 1 education plus u, observed variable, right? So we want to study how y varies with changes in x. So this is how you should interpret this linear regression model. So we want to study how weight changes if I change education, not the other way around. So be careful, the causality is important. I have to read it like this. If education increase or decrease by 1 unit, what will happen to wage? Okay. If gender, well, if you're talking about male versus female, what will happen to wage? If you're talking about different years of experience, what will happen to wage, right? So that's the causality, right? And mathematically, we can write it like this. We say if x changes by 1 unit, so if x changes by 1 unit, so what is delta x? Delta x is equal to 1. Then if delta x is equal to 1, what is delta y? It's going to be equal to beta 1, right? So we read it like this. If x or independent variable changes by 1 unit, then y is going to increase or decrease by beta 1 units. If beta 1 is positive, it's going to increase. If beta 1 is negative, it's going to decrease by beta 1 units, right? However, as long as we have this equation, as long as, delta u over delta x is equal to 0. So how do we interpret it in simple English? We say that this interpretation of if x increased by 1 unit, y is going to increase or decrease by beta 1 unit only holds if all other things remain constant or equal. So in another term, if delta u is 0 for changes in units of x. So mathematically, actually, I'm going to leave it as an exercise. That's why that's the case. We need this delta u divided by delta x is equal to 0. And in the class, I'm going to go over the proof of that exercise. But you should remember, so how do I interpret, for instance, this beta 1? I have to say, if education increased by 1 unit, then wage is going to increase or decrease by beta 1 units only if everything else is constant, or holding everything else constant. And here is what we mean by everything else, unobserved factors. So beta 1 is a slope parameter holding other factors in u fixed. Beta 0 is intercept parameter, also called a constant term. And the simple linear regression model is rarely applicable in practice. So let's think about it. Why? Why we rarely use simple regression model in real world? Well, the simple answer is that there is a very good chance that your y variable depends on more than only one independent variable, right? So wage depends on education, yes, but we know that it depends on many other variables that we are missing them, right? So that's why in practice, so this is a simple answer. In practice, we don't use simple regression model. We go beyond simple regression model. In more technical terms, why we don't stick to simple regression model? Because this assumption is not going to hold. So remember, in our example here, wage was a function of education. We called everything else constant. So here, everything else include maybe experience, include gender, and etc. And there's a good reason that if I increase or decrease the education, it's going to have some correlation with experience as well, right? So the more educated you are, and if I look at people at the same age, the more education they have, the less experience they got at work. Does that make sense? Because they have been studying instead of working. Okay. So there is a good chance that if I change education, then U is not going to remain constant. So for that reason, we say that we rarely use simple regression model in practice. However, its discussion is super useful, super useful, because we're going to drive all these calculations for instance, beta had 0, beta had 1, and etc. We're going to do all the analytics behind the regression analysis by using simple regression model. And when we learn how we do things in simple regression model using only one x, we can easily expand it to multiple x's and go to multiple regression model. Okay, So in chapter 2, we're going to only stick with simple regression model, make sure that we clear all the assumptions and all the formulas. And then in chapter 3 and 4, we will move on to multiple regression analysis, which is more fun. It's going to be more applied. All right. Now let's look at a couple of examples from the textbook. So imagine we are regressing, and sometimes I call it regress Y on something. So this is how you read it. We are regressing yield on fertilizer. So you want to see what is the impact of fertilizer on different on yield, on the soil yield, versus soil yield. Then we only control for fertilizer, but we know that yield has something to do with lots of other explanatory variables that we're putting them in unobserved factor. We just call it U. What are some examples? Rainfall, land quality, temperature, and things like that, right? So we are dumping them all and putting them we just call them unobserved. Again, if you have information for rainfall, land quality, and etc., it doesn't make sense to exclude them from the model. But here, for simplicity, we're going to exclude them from the model. And then in chapter 3, 4, we're going to say that we're going to control for as many control variables as possible. Okay. But here, let's stick to the interpretation. How should I interpret beta 1? In example number 1, beta 1 measures the effect of fertilizer on yield, holding everything else constant, all other factors fixed. Okay, so that's how we interpret that. How we interpret this beta 1. Beta 1 is the effect of education on wage, holding everything else constant. So if you increase education by 1 year, what will happen to wage? The wage is going to increase or decrease by beta 1. Again, if beta 1 is positive, it's going to increase. If it is negative, it's going to decrease by beta 1. The key is holding everything else constant. So we are assuming that this interpretation makes sense only if holding everything else constant is valid. So in simple regression model, we know for a fact that there is a very, very slight chance that we cannot hold everything else constant. Okay. So that's why, again, in practice, we don't use simple regression model. So what are some examples of U here? So we named a bunch of them in the first slide, but some other ones are labor force experience, work ethics, intelligence, and etc. Okay. All right, now let's see, when do we have causal interpretation between Y and X? Remember, this is something that we talked about from the first class to say, in econometrics, we hope we go from simple correlation to causation. At the end of the day, I want to see if if education is going to impact wage in a meaningful way. It's not just chance, it's not just random, right? So in order to move from correlation to causation in econometrics, we need to think of two assumptions. So assumption number 1 is, on average, those things that we call them unobserved variables, on average, they shouldn't matter. So the expected value of U should be equal to 0. So and as long as there is a beta 0 in our model, then we get the expected value of U is equal to 0 without loss of generality. Think about it, and I'm going to prove it next class when I see you guys face to face. But give it some thoughts. So why, as long as there is a beta 0 in the model, even if the expected value of all those unobserved variables is not 0, so we can make it to become 0. So this is a mathematical fact. So this is assumption number 1. Assumption number 2, we need to have mean independence. Remember, we talked about the strong independent, then which implies to mean independent, which implies to 0 correlation. So here we say that all those unobserved factors must be mean independent of your X variable. So all these unobserved factors here, like intelligence, in this example, gender, experience, and etc., whatever is not here, we assume that on their average is independent of education. So we call this assumption 0 conditional mean assumption, and it is going to play a huge role in our econometric interpretation, causal interpretation. So we have to read it like this: the explanatory variable must not contain any information about the mean of the unobserved factor. So let's go back to our example when we regress wage and education. So here we basically say that all those unobserved factors has nothing to do, their average has nothing to do with education. So if I look at the conditional expectation of all these unobserved factors given education for different levels of education, they should be equal to 0. Now let's pause for a second. How strong is this assumption? Remember, I said that we need to have two assumptions. On average, all those unobserved factors don't matter. Then their average is independent of the explanatory variables, right? So when I look at this equation in a simple regression model, do you think that this assumption is going to hold? Do we have zero conditional mean assumption? Remember, if I don't have this zero conditional mean assumption, then I'm less confident to say that the education has causal effect on wage. Maybe that's just chance. And unfortunately, it's the case because I'm only controlling for education, and then the chances that the expected value of these u's conditional on education is 0, it's very, very little. And the conditional mean independence assumption is very unlikely to hold. Why? Because individuals with more education will be more intelligent on average. Remember, this U contains some intelligence in it, for example, and we know that there is a relationship between intelligence and education. So I cannot assume that on average these intelligence here that we are looking at is independent of education. So for that reason, again, when I have a simple regression model only having one explanatory variable, there is a good chance that this is pure correlation. That's completely random. It's not causation. Or, put it in a better way, we are less confident to claim that there's a causal relationship between education and wage. So what's the solution? The solution is we have to control for more explanatory variables. So for instance, in next chapters, we're going to look at, we have to put this intelligence in the model. We have to put gender in the model. We have to put experience in the model. And then how far should I go? Why not including 100 explanatory variables? So this is a separate question. So it comes with a cost that we're going to explore in future chapters. All right, so let's stop here. I'm gonna make a new another video, and we will start talking about a population regression function and sample regression function.